Now let's see what is optimization with constraints. Normally in real life, there will be no optimization without a constraint. Everywhere it will be optimization with some constraint over there. For example, you go through the small scenario here. A hiker hikes on a mountain. Mountain I can describe through a mathematical way, like a surface z equal to f of x y, and it's given by a root of 1 minus x square minus y square, meaning z square equal to 1 minus x square, meaning x square plus y square plus z square equal to 1, meaning it's like a semi-sphere sort of thing, right? And he hikes, the path he goes on this mountain is this red path. Okay, right. So what's the question? What is the maximum and minimum height he reached during his journey, right? And where it happens? What is that point? What is the address of that point? Is one scenario. Okay. So now, if I want to formulate this mathematically, I have to optimize with respect to that red topographic map, right? So this problem is find the maximum and minimum of fxy equal to root of 1 minus x square minus y square subject to the constraint x square plus y 4y square equal to 1. The red path, its contour is an ellipse over there, right? Or in general, the structure of a constrained optimization problem will be find maximum or minimum of f of x, y, z, and variables can be there subject to the constraint g of x, y, z equal to some constant over there equal to c. There are many algorithms. One algorithm what in our syllabus or we want to discuss is Lagrange's approach. What Lagrange says is construct a new function, capital F of x, y, z, combining these two functions, objective function and the constraint. Then we can have the same algorithm, the same approach, what the way we approached in our unconstrained way. Okay, so this is what we are going to do. So the working rule is f of xyz is objective function, phi of xyz is the constraint, construct a new function capital F, which is a combination of f of the constraint and the objective function. So capital F is f of xyz plus lambda times some phi of xyz. Here lambda is called the Lagrange multiplier. Then get the critical points. How? Gradient del capital F to 0, mean dou f by dou x equal to 0, dou f by dou y equal to 0, dou f by dou z equal to 0. Then solve the above equation together with the constraint phi of x, y, z equal to 0. Right? The values of x, y, z so obtained will give the stationary value of f of x, y, z over there. Right? So the algorithm is construct a new Lagrange function, capital F equal to small f of x, y, z plus lambda times phi of x, y, z, then get the stationary points over there, then solve with intact with respect to the constraint. For example, here is an example. A rectangular open box at the top is to have volume 32 cubic feet. Find the dimensions of the box requiring least material for its construction. Okay, let x, y, z be the dimensions of the box. Then you know, since it's open at the top, you know surface area equal to xy plus 2yz plus 2xz. Now, the volume that is to have, I mean, the volume should be, there's a constraint here, no? Open at the top is to have the volume 32 cubic feet. So volume is xyz equal to 32. That's fixed. That's the constraint. Now, with this constraint, we have to find the least material, least dimensions over there. Okay. So what we do is we'll find a new Lagrange function, right? or this can be, there are two approaches here. One approach is reduce it to unconstrained problem, like uh, xy plus 2. You can, what I mean is, in place of a z you can plug in 32 by xy, and then it becomes a problem in xy. Then you can have old approach here, right? So dou s by dou x equal to what? Dou s by dou y equal to this. Solving these two, you get x equal to y equal to 4. Then get the Hessian, and it's the old approach. Okay, right. Now let's see how to solve with the Lagrange method. What does the Lagrange method say? Is form a Lagrange function. What is the Lagrange function? Capital F equal to xy plus 2yz plus 2zx plus lambda times xyz minus 32. Get the stationary points of the new Lagrange function. Dou f by dou x equal to 0, dou f by dou y equal to 0, dou f by dou z equal to 0. Call it equation 1, equation 2, equation 3. Somehow solve these three with respect to the constraint. Right? What is the constraint? X, y, z equal to 32. Now multiplying 3 by x and 4 by y and subtracting, we get 2zx minus 2zy equal to 0, or x equal to y. Right? And again, multiplying 4 with y and 5 with z and subtracting, we get y equal to z. Right? And we know that x equal to y, and we know that y equal to 2z. So the dimensions of the box are x equal to y equal to 2z equal to 4. Now plug in this into the constraint. Now, what happens? Plug into the constraint, then it will pop out x equal to 4, meaning y equal to 4, meaning z equal to 2. Okay. Let's do another example. Given x plus y plus z equal to a, find the maximum value of x power m, y power n, z power p. So the objective function is x power m, y power n, z power p. The constraint is x plus y plus z equal to a. Okay, so f of x, y, z in this case is x power m, y power n, z power n. Z power p. And the constraint is y of x, y, z equal to x plus y plus z minus a equal to 0. Construct a new Lagrange function. New Lagrange function is capital F of x, y, z equal to small f of x, y, z plus lambda times y of x, y, z. That equal to x power n, y power n, z power p plus lambda times x plus y plus z minus a. Right? Find the stationary points. Dou f by dou x equal to 0, dou f by dou y equal to 0, dou f by dou z equal to 0. Right? Then which yields m into x power m minus 1, y power n, z power p plus lambda equal to 0. Similarly, dou f by dou y equal to 0 says n into x power m, y power n minus 1, z power p plus lambda equal to 0. And dou f by dou z equal to 0 says p into x power m, y power n, z power p minus 1 plus lambda equal to 0. So from these three things, you can pull out lambda, and all the three lambda should be equal. The first one, so from the first one, minus lambda equal to m into x power n minus 1, y power n, z power p, and that in turn equal to n into x power m, y power n minus 1, z power p, and that in turn equal to p into x power m, y power n, z power p minus 1. So that gives the lambda. So all the three are equal. Now, just making use of x plus y plus z equal to a, shuffle them, you get m by x equal to m by y equal to p by z equal to m plus n plus p by x plus y plus z, that equal to m plus n plus p by a. Therefore, the maximum value of f occurs when x equal to am into m plus n plus p, right, and y equal to an by m plus n plus p, z equal to a p by m plus n plus n. Hence the maximum. So that's where the maxima occurs. So putting that value in f, the function f of x, y, z equal to a power m plus n plus p into m power m into n power n into p power p by m plus n plus p whole power m plus n plus n, m plus n plus p. That gives the maximum value. Okay. So what is the algorithm? Pretty simple. Understand the problem there. take it onto your mathematical domain, understand the objective function, call it f of x, y, z, or whatever. Understand the constraint, call it phi of x, y, z. Then form a new Lagrange function, capital F, which is a combination of the old objective function and the constraint. That is capital F equal to small f of x, y, z plus lambda times phi of x, y, z. Find the stationary point of the new function, capital F, like the f by dou x equals 0, dou by dou y equals 0, dou by dou z equals 0. Then those three coupled with the constraint will yield you the maximum point or a minimum point. Okay, so we'll do some more problems in the next class. Just go through the problem here, you can understand.